So let's suppose that we want to find all the different stereoisomers of the sugar aldotetrose. So let's begin by determining what the structure is of aldotetrose. So the aldo part of aldotetrose means that we have an aldehyde. So the top portion of the straight chain sugar contains a carbon-oxygen double bond as well as an H atom. This is our aldehyde portion given by this aldo. Now we have a total of 4 different carbons because tetrose means 4. So 1 carbon, 2 carbon, 3 carbon, and 4 carbon. The final carbon of our aldotetrose, or any aldose for that matter, contains the primary alcohol group. So we have this carbon bonded to 2 H atoms as well as to our hydroxyl. Now, what about these 2 carbons? Each one of these 2 carbons contains 2 different groups. We have an H atom as well as the hydroxide. So let's suppose that this particular stereoisomer contains our 2 OHs that point to the same side, to the right side. And so on this side, we have our 2 H's. Now, the question is, this is one stereoisomer, how many are there? So to calculate the total number of stereoisomers, we have to determine how many stereogenic carbon atoms we have on the aldotetrose. So this carbon is not stereogenic because it does not contain 4 groups, and this one is not stereogenic because out of these 4 groups, 2 of them are exactly the same. But these 2 carbons are stereogenic because they each contain 4 groups that are different. So we have 2 stereogenic carbons, and that means we can use that information to calculate the total number of stereoisomers by using this equation. So 2 to the power of n, where n is the number of stereogenic carbons. So this means 2 to the power of 2 because we have 2 stereogenic carbons. And so we have a total of 4 stereoisomers of the aldotetrose. Okay, so now that we know this and we know one of these isomers, let's determine the other 3. So this is part of a category of molecules known as the D-aldotetrose, and that's because this last stereogenic carbon contains the OH group that points to the right side. So in fact, the second molecule, the second stereogenic carbon, will also be a D-aldotetrose, but in this case, our hydroxy group on this carbon will be pointing to the other side. So this is the second stereogenic carbon that we're going to have. And both of these molecules fall into a category known as D-aldotetrose because the D part means tetrose, because the D part means these 2 hydroxy groups, or this hydroxy group on the final last stereogenic carbon right next to our primary alcohol group points to the right side. Now we can also look at the L-aldotetrose. The L-aldotetrose contains the OH pointing to the other side, to the left side. So that means we have our aldehyde group as always, and on the final carbon we have our primary alcohol. Now because we're looking at the L-aldotetrose, our OH now points this way, and let's suppose that the OH on this carbon also points this way. So this is another stereoisomer, and the final stereoisomer is also our L-aldotetrose, but in this case, this group basically points in the other direction. So this OH group still points this way, but now this carbon has the OH group that points in the other direction. So these are the 4 different types of